Okay, welcome back, Harun. So in today's video, we're going to be talking about the infimum and the supremum of the set. Now, I guess I've recently been looking at real analysis, so I'm going to make a few videos about the topics that I find pretty interesting. So today, I guess the core idea of real analysis is the supremum. It's very important, at least in your first course in real analysis. Um, it's a building block, obviously, for the least upper bound property, which I'll be talking about in later videos, and we'll actually be proving it as well. Um, uh, so now, well, in order to get a taste of a bit of abstractness involving what we're gonna a later proof that we're gonna do in this episode, we're gonna quickly prove this pretty simple fact, and it's just to get an idea for this statement for all epsilon greater than 0. So the theorem goes like this. A equals b if and only if the absolute value of a minus b is less than epsilon for all epsilon greater than 0. And a and b are real numbers. Okay, and I should be a bit shameful here because we're actually already working with the real numbers, which is kind of cheating. But later on, we're going to actually, and probably in the next one of the next few episodes, we're going to be defining the real numbers in terms of Dedekind cuts, and maybe later in terms of Cauchy sequences, which is a better way of doing it. But for now, we're just going to stick to Dedekind cuts. And oh, sorry, that's spoilers. We're going to be working through these examples in later episodes. Okay. Oh, actually, I kind of revealed that a bit. Anyway, hopefully you didn't look at that. So let's prove this statement here. Well, first, it's an if and only if statement. So first we want to show this direction. So if a equals b, then we want to show that this is true. So if a equals b, well, plug in that into this, we're going to get, or just note that, well, notice that absolute value of a minus b is just going to be absolute value of 0, which is 0. So notice that well, we have that there surely exists an epsilon greater than 0 such that this is the case. So for all epsilon greater than 0, this is true. So that is what we wanted to prove for this direction. So clearly this direction is quite simple. So now let's prove it in the other direction. So we're going to strive for a contradiction in this case. So, well, let's see. By way of contradiction, suppose a is not equal to b. Well, what does that tell us? That tells us that a minus b, since it's always going to be not negative, but since a is not equal to b, this is actually greater than 0. But actually by the density of q in the reals, which we're going to be proving after we define Dedekind cuts, then actually there surely exists a rational epsilon here, such that epsilon is actually less than a minus b, and this should be also very intuitive and greater than 0. But notice that this is a contradiction, since we actually assume that, well, for all epsilon greater than 0, this holds. Okay, so that's kind of the idea. And if you're not really that comfortable with that, you can also think of it as just literally taking epsilon equal to this, right? Because it's for all epsilon greater than 0, and this is clearly a real number, right? So we can take this to be epsilon, but then if we plug that into here, then we have that a number is greater than itself, which is a contradiction. So that's another way to think about it. Okay, so that completes this little proof here. So now what are the infimum and the supremum? So I'm going to get rid of some of this. Okay, well, first let's start with the supreme. Let's consider some set S, okay? Then we say that little s is the supremum of capital S. If, well, first of all, maybe we should define what an upper bound is. So an upper bound for a set S is, let's say, some u, let's say in the real numbers, such that for all s, little s in S, we have u is greater than or equal to s. So that's what an upper bound is. The name clearly implies what it is. It's an upper bound for the set. Okay? But what the supremum is it's the least upper bound. So notice that there are going to be infinitely many upper bounds for a set. So if we have one upper bound, then all the elements greater than the upper bound are also upper bounds. So we have infinitely many upper bounds for most sets. Well, most sequences, I should say. But again, what the supremum is, like I said, it's the least upper bound. So that tells us that there is no. So if we take any u prime less than u, or I guess we should say like, so let's say k, let's say n is the supremum, and this is how we write supremum. So if n is the supremum of S, then if n prime is less than n prime must be in S. In other words, well, I guess to be more specific, I'm too used to Dedekind cuts, which you'll see later, but n prime is not an upper bound, not upper bound. So for any n prime less than n prime is not an upper bound. For S, of course. So it's the least upper bound. That's the intuition for that. And let's consider the infimum. It's the same idea, but in this case, it's the greatest lower bound. So if we have like this set, if you visualize a set, so we have, for example, here would be the supremum. Let's say it's somewhere here, and then the infimum would be somewhere here. So if we take any little element less than that, it's going to be either, in, or here. If we take any element less than the supremum, it's either going to be in S or not an upper bound at all. Like, it's not going to be an upper bound. It's just going to be outside of S, but to the left of the supremum, okay? And for the infimum, it's the greatest lower bound. So notice that these are all lower bounds. There are infinitely many. Respectively, there are infinitely many upper bounds. But if we take any element greater than this greatest lower bound, it's going to be either in S or somewhere here, right? Okay. So that's the idea. So now we're mostly going to be working. It's kind of funny how the supremum is so much more important than the infimum, it seems, but yeah, that's kind of just how it is. So we're going to actually look at this nice definition, this nice result of the supremum, which is in terms of epsilon. So we're going to prove the following. We're going to prove that S equals the supremum of capital S, where S is a set that is bounded above, I should say. If and only if, for all epsilon greater than 0, there exists an A in S such that S minus epsilon is less than A. So proof. First, again, we're going to prove it this way. So if so we have that S equals the supremum of capital S. Okay, well, since epsilon is greater than 0, we take epsilon greater than 0, we note that s minus epsilon is less than s, right? So if we subtract this, this just tells us that epsilon is greater than 0. So if and only if epsilon is greater than 0. So it's a true statement, and therefore this is a true statement. Okay. Well, how do we go from here? Well, let's see. So notice that we want to find an A such that s minus epsilon is less than A. So, well, let's see. So actually notice that s is the supremum, so s minus epsilon has to be in s, right? So s minus epsilon is in s. Therefore, well, I guess I should say that to be specific, s minus epsilon is not an upper bound for s. So, in other words, that just tells us that there exists an A in S such that S minus epsilon is less than A. So this is what we have. And okay, that shows it that way, right? Because that's what we wanted to get to. So that shows us that way. So, well, let's see. Oh, I did it again. So to show it the other way around, in other words, this way, we now know that s minus epsilon is less than A. For all epsilon greater than 0, there exists an A in S such that this holds, and we want to show that this implies that S equals the supremum of S. Now, by way of contradiction, suppose S is not equal to the supremum of S. Okay, well, that tells us that there exists, let's call x prime, such that S prime is less than S. Okay, and S prime is an upper bound for S. Well, now let's take epsilon to be equal to S minus S prime. Okay? Well, now let's actually plug that into here. So when we plug that into there, we actually just get that S prime is less than A. But that's a contradiction because we assume that S prime is an upper bound for S. But we found an A such that S prime is less than A. So that tells us that S prime is not an upper bound, and that's a contradiction again. So this is a contradiction, right? And that tells us that S equals the supremum of big S. Okay. So that's the idea of this proof. So this is a nice little theorem. And now I guess for last little thing before we get to the juicy examples, let's kind of just look at some really simple ones. So let's look at these simple little sets. So we have, well, let's look at this interval. Now I encourage you to try to find the infimum and the supremum, and the maximum and min. And I should say that the max, I should have defined this earlier, but the maximum is an element, call it M, in our set S, such that for all S in capital S, S is less than or equal to M, capital M. And respectively for the min, it's the same thing, but let's just take n to be, in S, such that for all S in S, n is less than or equal to S. So that's the min. Now the difference between max and min is this right here. That's a key difference. M is in S, but the supremum, as you'll see in this example, doesn't have to be in S. It doesn't have to be in S. But if the max and min exist, so if the max exists, then that's the supremum. If the min exists, then that's the infimum. So let's look at that with this example, and then we'll close the video. So what is the infimum? The infimum, well, and also the max. Let's first look at the max. We start off simple, or the min. Let's start off with the min. So the min, well, the least this interval we get is 0. And since the min exists, this is also the infimum. So now consider the max. Well, showing this rigorously is a bit, well, it's not very difficult, but we can do that maybe or maybe we can try that right now. We'll try it right now, but I guess what I'm trying to say is that the max, there is no max, and I guess we can show that. But we notice that the supremum is going to be 1. But to show that there's no max, it suffices to show that for any element, say S, in that interval, then A, I should say, then there exists a prime in, let's say, the interval I, such that A prime is greater than A. And we're working the real numbers here, okay? Well, this is actually not too bad, because notice that we can actually just take A prime to be equal to 1 plus A over 2. And I'll leave it to you guys, I'll leave it to you guys to show that not only is this greater than A, but it's also less than 1. In other words, it's going to be in A. It's going to be in our interval I, and it's greater than A, so there is no maximum. And then using a similar method, you can show that 1 is actually the supremum. Okay? Well, actually, this should suffice. Just showing that there is no maximum here, and should suffice to say that 1 is the supremum. So max doesn't exist, but the supremum is equal to 1. Okay, well, that should be good enough for now. I hope you enjoyed the video, and in the next video we'll look at the below examples. This one is actually the most interesting here. It's going to take the most effort, but the other ones shouldn't take as much. So I'll see you then.